Hello, my name is Scott Lapierre. I'd like to thank the conference organizers for inviting me to participate today. I am presenting an integrated workflow for predetermining recoverable oil in place and its application to well spacing optimization. Now, the shale industry is deep into the process of infill drilling and determining optimal well spacings. Now, in general, we might agree an optimal well spacing is one that maximizes recoveries per well, per acre, and per capital dollar, all while minimizing well interference. And in today's environment, we should also consider it one that generates the least amount of CO2 from the D&C process to release into the atmosphere. Now, trial and error well experimentation can be highly capital destructive with just one failed iteration. So reliable methods for predetermining optimal well spacing are needed, not only to ensure that today's capital will be adequately offset by tomorrow's revenue from production, but also to achieve our ESG targets by avoiding overcapitalization and the associated unnecessary consumption of natural resources and excessive release of CO2 from the unnecessary D&C processes. The basic concept of the workflow I'm presenting today is as follows. We will leverage the plethora of available core measurements to generate an oil in place with minimal uncertainty. Then we will leverage recent developments in reservoir engineering to actually predetermine available recovery factor directly from first principles. By combining oil in place with recovery factor, we will derive a recoverable oil in place for a given drilling unit. Then we will use this recoverable oil in place to explain production from a real-world development program and also use it to design more optimal combination of well spacing and stimulation intensity. The keys to generating and validating low uncertainty oil in place start with core measurements. Now at present, many disparate measurements are available. However, they rarely are found to agree closely in terms of hydrocarbon fill porosity. But by reprocessing and correcting key measurements for known shortcomings, we can reveal close agreement between disparate techniques and then use these to calibrate multiple independent petrophysical and geochemical workflows, and thereby more precisely reduce the margin of error in our estimates of hydrocarbon fill porosity. One of the critical corrections that needs to be applied pertains to GRI type measurements. Specifically, they are often inflated due to rampant core expansion at surface. We often see this as poker chipping or as unnatural partings in cores, plugs, sub-millimeter scale, and also the sub-micron scale. Unfortunately, the standard math of the GRI process attributes these parting volumes, these expansion volumes, directly as hydrocarbon content. So I apply the corrections published by Dylan Collins and myself from 2014, which showed that raw GRI can overestimate hydrocarbon concentration by 200%. Now that's a big margin, and we certainly want to look to other core measurements to validate our course of action. And program pyrolysis is actually the most direct, verifiable, and repeatable measurement that we can make of hydrocarbon content. It doesn't receive the attention that it deserves, primarily due to petrophysicists like myself, geochemists, geologists, not being that familiar with the translation from reservoir conditions to stock tank conditions as easily as an engineer is. It also has a lesser known problem, and that is that the mobile hydrocarbon fraction that we're interested in is not just in the S1 peak, but is also in the low temperature shoulder of the S2, which requires solvent extraction to capture. So I like to employ the solvent extraction and math for deriving hydrocarbon fill porosity from pyrolysis, published by Dylan and myself in 2014. And what's really cool about this is we begin to find support for our other correction. In other words, solvent extracted pyrolysis is found to more closely agree with GRI corrected for core expansion. But we still need more. So as a third source of constraint, I like to integrate the estimation of Kerogen porosity as a function of thermal transformation, according to the work that Chris Modica and I published in 2012. Now, in a nutshell, all we did here was translate several decades of established geochemistry from the weight fraction domain into the volume fraction domain. That's really all this is. But what's really exciting about this is that The Kerogen porosity estimation closely agrees with both the solvent extracted pyrolysis and the GRI corrected for core expansion. So now we have 3 independent measurements that closely agree, and we can begin to quantify our margin of error in a meaningful way. But more importantly, we can also decide that, you know what? The likeliest value for hydrocarbon-filled porosity lies within this range. So we can use these data to calibrate our petrophysical models. Now, I have an elaborate integrated workflow here of a bunch of imperfect petrophysical workflows that together, when calibrated to all of the disparate core measurements, can provide an uncertainty minimized hydrocarbon pore volume or hydrocarbon fraction. And you can pause this and read it, but essentially I use multiple redundant methods to derive key parameters such as Kerogen porosity, and then I in parallel process for water saturation and porosity based on an Archie type process to compute hydrocarbon filled porosity, which I calibrate to the GRI corrected for expansion. And these combine into a composite to provide an uncertainty minimized hydrocarbon fraction. And it also allows me to leverage all of that expensive core data that we paid for. Now, we bring the geologist in to map our average properties and our net thickness of an important interval and derive hydrocarbon pore volume in terms of reservoir barrels per square mile. Then we turn to the engineering fluid properties correlations to convert reservoir barrels per square mile into stock tank barrels per square mile. And there we have oil in place triangulated by multiple approaches from multiple disciplines. Now, one of the beauties of this approach is that when you go to computer contour these data, they often contour up very intuitively. And the final map very closely resembles the initial map after a minor amount of QC process where the petrophysicist goes back and investigates the extremes, or the pimples, as I like to call it. And usually in that process, we identify blatant log quality issues or clear mistakes in the petrophysical interpretation process. Another thing that happens when you work things this way is that in the past decade of employing these workflows, I have discovered some remarkable relationships between things like Archie's parameter N and thermal maturity. I've also been able to extend Passey's delta log R beyond the original intended oil window range deep into the dry gas window by correcting LOM for resistivity retardation with overmaturity. Now, those are great benefits, but the benefits of working this way also have revealed that there are really strong relationships between initial GOR and initial API with thermal maturity. And in fact, discovery of initial reservoir pressure gradient being highly correlated to Kerogen transformation ratios has allowed me to contribute more substantially to the engineer's challenge of determining optimal well spacing. When we combine these developments with recent developments in reservoir engineering, specifically related to reservoir drive energy, we can become even more directly predictive and explanatory of existing production. In 2017, I published an article discussing implications of oil expansion being primary source of energy driving production to the surface. And a couple of weeks later, actually, Koshkadem et al. From Texas A&M, with Professor John Lee included, published work that independently and indirectly supported my notions. As seen here in their figure 3, where you have pressure normalized rate plotted logarithmically against material balance time, they were using established reservoir theory to predict that the degradation of transient flow will occur in coincidence with an escalation in GOR as the reservoir transitions over to boundary-dominated flow. But interestingly, they also output reservoir pressure simulation. And they inadvertently proposed that the very beginning of the degradation and transient oil decline and the very beginning of the escalation in GOR are tied to the exhaustion of oil phase expansion upon the achievement of bubble point. This is very interesting because oil expansion can be determined fundamentally from first principles. As illustrated in this cartoon phase diagram and the formation volume factor plot from PVT data, a stressed volume of oil will undergo a subtle and slight enlargement as stress is removed from the depletion process. Once that pressure is reduced to the bubble point, the shrinkage terminates abruptly as the expansion terminates abruptly as shrinkage sets in and solution gas is effervesced to become the separate gas phase. So essentially, we're able to consider the pre-bubble point production as the fractional enlargement of a stimulated oil volume inside of a stimulated reservoir volume while stress is relieved with the onset of production. So we can determine this amount of enlargement from first principles. And the magnitude, or excuse me, the oil expansion or oil compressibility drive is governed by the magnitude of undersaturation pressure and the average fluid compressibilities. Now, in light of a newfound respect for the fact that the majority of work is done by our reservoir over this pressure range, I like to refer to this pressure as working pressure, and I denote it with PW. And importantly, existing legacy lab services exist for us to entirely and thoroughly constrain the calculation of recovery factor at bubble point. Once we constrain this, we can map it. And here is the map of recovery factor for the Wolfcamp A and B across the Midland Basin. When we combine this recovery factor map with our oil in place map, we derive a map of recoverable oil in place. And in my personal experience, this is the mother of all treasure maps. In fact, this was the foundation upon which my company P-Core was founded in 2014 and resulted in our successful delineation, grassroots leasing, proving, and divesting of a high-value core asset in 2016. So I've practiced these in the field, and they work well. Now let's look at application of this concept to real data. In 2019, the Wall Street Journal wrote an article about a cube development in south central Midland Basin. And here I've extracted the data, and you can see that there are 15 wells devoted across 3 landings to drain the Wolfcamp A and B across a drilling unit of 542 acres. So I determined that for that 542 acre drilling unit, the recoverable oil in place is 47 million stock tank barrels. I then determined that the primary drive mechanism is good for a recovery factor of 6.99%, and that multiplying these two together reveals that 3.3 million stock tank barrels are available for recovery from this drilling unit. And this suggests that the 15 wells would each recover about 221,000 stock tank barrels, assuming 100% of the recoverable oil in place was connected inside of a stimulated reservoir volume. Interestingly, when we look at historical production, over 1,600 days of production from these wells, we see that the reservoir collectively has transitioned to boundary-dominated flow, consistent with the work of Koshkadem et al. And unfortunately, these wells are headed towards a recovery of about 210,000 barrels apiece, which represents a 70% shortfall from the published corporate expectations. Now, as it turns out, the indicated ultimate oil recovery from these empirical observations is explained within 95% of the theoretically derived 210,000 stock tank barrels. And that's quite encouraging. This seems to have some promise in this one application. if I had more time, I would show you others. The as-drilled program wasn't a total loss. It manages to generate $28 million in profit on a capital spend of $106 million. But this 14% IRR is only good for 8 years, as each well dies competing with each other to drain the same reservoir. However, if we widen the spacing, reduce the well count, but increase the completion stimulation intensity to achieve the same drilling unit stimulation efficiency, we should be able to generate a $78 million profit off of only a $57 million spend. And this 22% IRR will last us 40 years and provide plenty of revenue to both pay dividends and also invest in future growth opportunities. But also importantly, with the optimized program, we will be consuming only half of the natural resources and releasing only half of the CO2 into the atmosphere from the D&C process, while delivering 3 times the profit and 3 times the lifespan. So this is an encouraging consideration. So in conclusion, I hope I've inspired you to leverage all your core data to objectively minimize uncertainty in your oil in place determination. I also hope I've encouraged you to discover the many very useful universal relationships that exist between key parameters that you'll discover upon reprocessing all of your legacy core data. And finally, I hope you're enticed by the ability to explain actual production to within 95% and possibly optimize future development programs so that our industry can be as economically and as environmentally sustainable as possible. If you have any questions, I am absolutely welcome for your contacting me and asking questions at this time. Thank you very much.